So this video is about how to model simple modeling of gravity forces, also known as weight forces, and this other type of force called a support or normal force. These end up being quite confusing because in a lot of cases, these forces have the same size as these forces, but they point in opposite directions. Sometimes people confuse these two as Newton's third law of pair forces, but they are not. Yes, and so let's get to it. So first thing that I'd like to point out is gravity is a special word. In fact, is the name of an interaction. That is, we say that two massive objects have gravitational interactions, like attractive ones. So you might say that the Earth and our little moon that travels around the Earth in an elliptical orbit, they are having an attractive gravitational interaction, which is why the moon and the Earth just sort of stay together, even though the moon is going around the Earth quite fast at a large distance of separation. These two objects, in some sense, they have a binding interaction. They're stuck together. They're stuck together because they are gravitationally interacting with each other close enough such that other things can't ruin this pairing. So the moon's been going around the Earth for a really long time in this very stable situation, or seemingly stable situation. But anyways, there is another word that's very special called the weight. And this word is actually the force. So gravity is the interaction, and the weight force is a force due to gravity. So that's me being really pedantic and careful. But what I'm going to describe is actually how to model the weight force. So this is how you model the weight force. It's really simple. The weight force, so force is a vector, is equal to the mass of the object whose weight I want to know. So this is the weight force acting on the object M, whose mass is M. You just multiply it by the acceleration due to gravity that M would have if it fell in free fall. So on Earth, the acceleration due to gravity is 9.8 meters per second squared. The acceleration due to gravity is a vector, and it's down like this. So, all right. So as an let's see, yeah, as an example, let's say that the mass of an object is, let's say, 67 kilograms. This mass, this amount of mass, is roughly, say, an average person. So an average person has a mass of around 67 kilograms. Yes, so let's calculate the weight of this person. So the weight, I'm going to do something interesting. So this actually is the way you calculate a weight force. A force is a vector, so this is a vector calculation. Scalar times this vector acceleration is this vector force. But I'm going to calculate something, it's probably what is shown to you in your book. Your book says W equals m times g, likely. I showed you the vector version, but this is the scalar version. This just comes from the fact that if you take the magnitude of both sides, so the magnitude of W is this thing called W, it's equal to m times g, which is m times the magnitude of g. This is just the magnitude. It's just taking this equation and asking the magnitude on both sides. But let's calculate what is the weight of an average person. Well, it's 67 kilograms times on Earth, where average people are, the acceleration due to gravity is about 9.8 meters per second squared. So if I put this in my calculator, so 67, you notice there's no button for kilograms, so I'm going to leave that out, times 9.8. Again, no buttons for meters per second squared because this does math and we are doing physics. But the math part of this physics problem comes out to, so I'm going to round 657. I know I'm not following the significant figures rule. I really ought to keep just 2 sig figs, so I'd put 66. Actually, let's go ahead and do that. So 66 kilograms meters per second squared. But this actually is, this combo is called the Newton. The kilogram meter per second squared is the definition of the force unit called the Newton. And so this says that the weight force is 66 newtons in magnitude. Okay, let's be really very pedantic though. This is, if I'm really careful and really thoughtful about it, this is a force that acts on the person who I'm going to identify as M. So this is the force on M. It is by another object. The other object is called the Earth. And the reason that these two things can have this interaction is because gravity exists in the universe. So this is really pedantic, but this is the force acting on M by the Earth due to gravity. It's also known as the weight force acting on M. Okay, so for fun though, that's not the only weight force that could act on M. Another weight force that could act on M is, what if the person is an astronaut and they go and visit the moon? So on the moon, the acceleration due to gravity, things fall. In free fall, they fall with an acceleration of about 1.6 meters per second squared. And so the weight force, or the weight of this particular astronaut, this very same 67 kilogram astronaut, I actually, going back a little bit, I just realized that I forgot a significant figure. It's 660. I mean, you can kind of see that this is about 10. This is about 60. This is 10 times 67-ish. So back down here. Sorry about that. So this is more like a 2, where that's a 10. So we expect to see a weight force with a number that's doubled on the astronaut's weight, roughly doubled. But anyways, you'll see. So take 67 kilograms multiplying 1.6 meters per second squared. So this is how we'll calculate. It's m times the acceleration due to gravity on the moon instead. This is the acceleration due to gravity on the Earth, like that. So back to the calculator. 67 times 1.6, 107.2, keeping only 2 significant figures. It's about 110 newtons, right? And if we wanted, we could say that this is the force on our astronaut called M, not by the Earth, but instead by the moon. And it's still due to gravity. It's the gravity interaction between the astronaut and the moon, 110 newtons. So this is a description of gravity. So really, very, very quickly, let me make clear something. So let's say that this is the planet, and I have the astronaut standing on whatever planet. So this weight force that's acting on the astronaut is headed down towards the center of whatever the planet is. It's a center-to-center force. So it's center-to-center directed. The direction is center-to-center. So they have some value of weight, W. So what's interesting is even if this astronaut is just a little ways above and falling or standing on a ladder, no matter how they're moving, if they're moving up or they're moving down, it's interesting to tell you that the way you model this weight force is no matter how they're moving, this weight force has always the same value in the same direction. That's the idea. So this weight force is independent of the motion and how the motion is changing. This is the idea. As we get further into the course, actually, we're going to learn how to more carefully model the gravitational interaction. For example, when this astronaut is very far away from the planet, their weight force is actually quite a bit smaller, and that's because the acceleration due to gravity when you're far away from the Earth is smaller than 9.8. And the further away you get, the smaller that value is. And then when you get infinitely far away from the Earth, this value is finally 0. The Moon has a different gravitational field close to its surface because it's got a different size as well as a different material makeup. That is, it's got a different density. It's got a different ultimate mass. So the mass of the Moon and the size of the Moon is different than the mass of the Earth and the size of the Earth. And that's why they have different acceleration due to gravity at their surface. But more on that later. What I want you to get from this is essentially how to use this. It doesn't matter the state of motion. The weight force is always on. Okay, so that's important.